Hello, what's up, you guys? This is TurboMind. This is one of the first videos I'm making for you. I just want to show you a little hands-on project on how to do an optimization on performance discipline of a turbofan engine. So we're not going to do this in depth. We're not going to do this in detail. It's just a demo, and we're going to see that how we are going to optimize our uh, pi cycle model of a turbofan engine, which in our case is the JT9D 7FW, which is a high bypass conventional twin spool turbofan, and the performance model has been made by PyCycle, as will be made obvious for you in the next videos that I will walk you through it. And then there's the performance code. Don't you worry about that. You're gonna know this. You're gonna learn how to do things like me, and even better than me. And there's the design points. And as you can see, some of these are commented. These are the off designs that I've commented. And we're going to take this model into the optimization and optimize a single objective performance optimization. Okay, so this is my MDAO code in the OpenMDAO. Don't you worry about that. We're going to walk you through it in the next videos if you were interested. This is just demo. I had to change my design and optimize it, so I thought maybe you'd like to see that. So this is gonna be doing. Okay, you don't have to learn all of this. Okay, so I'm just gonna show a little thing or two. So I've set up my whole model. I've imported the performance code along with other disciplines as well, but I'm gonna do single discipline optimization here. My design variables are fan pressure ratio, HPC pressure ratio, and a splitter dot bypass ratio. And these are the ranges, lower and upper bounds of each one. As you can see, add design variable to the model. And we're going to have our objective, design.performance.tsfc. So TSFC is the representative of the engine's performance that I have chosen as an output for the optimization. Our goal is to minimize this function and then see what happens. So, and as you can see, there's no constraints for now. I'm just going to run this. I have set up my whole model. Let's run this thing and see how that works. And my model is SLSQP, the driver model, the optimizer, the SLSQP, a gradient-based Newtonian optimization scheme, and we're going to use that. These are some options. Just let's run the code and see what happens. So this is going to use our performance code of PyCycle of the JT9D engine, which I have done minor changes to it, and I've validated it. And right now we're going to do a single objective optimization of the problem and see what will the TSFC be out. And I'm going to show you the actual TSFC of the performance model, which is called the MDA, multidisciplinary analysis, if there are other disciplines involved. So as you can see, it is trying to change the design variables. Each iteration and each function evaluation, it tries to evaluate the objective function, which in this case is the TSFC. As you can see, its value is changing and it's going lower and lower. And we're going to wait and see what happens in the next videos, in the next minutes or so. But in more detail, in the next videos, we're going to see what happens. And SLSQP works pretty fine with nonlinear constraint optimization problems. And that's it. Boom, done. So this is the code that I have written on. These are the actual results of the PyCycle when you get it. I have set my thrust level. The Mach is 0, the altitude is 0, the bypass ratio has converged to 6, the TSFC has came lower to the 0.30. And I want you to know that my actual TSFC was around 0.33, and this is the English system: pound thrust per hour, pounds of mass, or reverse. I'm gonna have to check it out again. You don't mind this. And yeah, that's it. As you can see, I have my TSFC, and the run is here. It's terminated successfully. The current objective value is this, 13 iterations, and the corresponding design variables are shown. We're both in the model and just by typing some print functions just down here that I have written. As you can see, optimization results. We're going to have HPC PR. We're going to have fan PR, prop.getVal design fan PR, and the 0 gets access to the actual value inside this list, if we could call it a list, and the bypass ratio, and then the other things, the parameters. So yeah, the HPC PR has reached to the upper bound of 7. Fan PR is somewhere in the middle, bypass ratio to the maximum, and TSFC to the lowest, which is in our case TSFC optimized, which I have written it right here, prop.getVal design perf TSFC 0.30. So that's it with the one of the first videos of the TurboMind channel, and you're gonna know the next things when I go through them. And I've decided to record videos to let you know how you're gonna work with PyCycle and OpenMDAO, because as you might know, some performance goes like PyCycle doesn't even have optimization, doesn't have even documentations that help you with your problem modeling and optimizations in the future. So I'm gonna let you know what happens, and this is it. Thank you. Please like and subscribe and comment if you like it.